Imagine how natural intelligence works. Whether it's a child learning to ride a bike or, a musician mastering a new piece, we learn continuously. It's moment by moment, real time, constantly taking in new stuff from this stream of experience. We sense, we act, we update, almost instantly. But here's the puzzle. If this continuous streaming learning is so fundamental, why has it been so incredibly hard, almost intractable, to replicate in deep reinforcement learning?
That is exactly the question. The central, really tough challenge that this groundbreaking paper we're diving into today tackles head on. Welcome to the deep dive where we unpack these complex ideas. And I'm genuinely excited to get into the details of this work with you.
Me too, absolutely. Today we're taking a close look at Streaming Deep Reinforcement Learning Finally Works by Mohamed Elsayed, Gautham Vasan, and Rupam Mahmood from the University of Alberta. And this isn't just, a small step. It feels like a really significant leap in how we think about adaptive AI.
Definitely. Our mission today, and this is really geared towards you, the listener, with your expert background in machine learning, data science, maths, is to really explore how this research identifies and crucially overcomes what they call the stream barrier. This barrier is just fundamentally blocked effective streaming deep RL. And by breaking through it, they've unveiled a whole new class of algorithms that really promise to shake things up for AI on device in resource-constrained settings. We'll dig into the technical hurdles, the clever solutions they came up with, and the solid empirical evidence showing they actually work. No glossing over details. We're going deep.
All right, let's unpack this. Starting with that idea of natural intelligence. It is so fluid, isn't it? Like you said, humans, animals. We don't collect a huge batch of data, go offline, process it meticulously, and then come back to act. No, you touch a hot stove, you learn right then. That feeling. Integrate it immediately. You don't stick it in some mental replay buffer to batch process later with all the other painful things that happened that day. It's immediate feedback.
Exactly. That natural parallel is precisely why the classic RL algorithms, things like Q-learning, TD learning, they were originally designed with this streaming idea at their core. Their initial setup was all about updating based on the very latest sample right away. No storing it, no waiting. And this immediate processing, this real-time adaptation, well, it's incredibly appealing for lots of practical reasons.
Oh, absolutely. And compelling reasons, too. This on-the-fly approach gives you huge advantages, especially in the real world where resources, compute, memory, power are tight. Think about edge devices, embedded systems, or even something like a Mars rover like Wang et al.
Yeah.
Mentioned in 2023. These aren't places where you have tons of memory or power to just store high-dimensional data like image streams or sensor readings for later replay. The memory needed for typical batch deep learning, it's just prohibitive there.
Yep. Right. And beyond just memory and power, streaming learning is also critical where you have serious communication limits. Maybe you're a remote sensor network or robots where sending loads of data back to a central server just isn't feasible, or maybe it's way too expensive. In those cases, learning directly on the device, streaming style, it's not just nice to have, it's often the only way. And, let's not forget privacy. Increasingly critical. Processing data as it arrives without storing it long-term significantly reduces privacy risks, data breach risks. Ven et al. Talked about this in 2020. No data sitting around to be compromised.
That's a really strong point on privacy. And then there's the huge benefit of rapid adaptation. If your system learns directly from its latest experiences, it can just adapt much, much faster to dynamic changes. Think about an industrial robot doing precision work. It starts getting wear and tear on its joints. It needs to adapt its movements now, not after some overnight batch update based on yesterday's data. This immediate learning from fresh experience is absolutely key for robust AI in the real world.
So yeah, given all these advantages and the historical roots in classic RL, you'd think streaming deep RL would be the main approach. But paradoxically, there's been this shift. Recent deep RL advancements, they've mostly relied heavily on batch learning.
Yes, there's a strange divergence, isn't it? If you look at the typical batch RL setup, and the paper shows this clearly in Figure 1A agents store past experiences, observations, actions, rewards, and next states, in a replay buffer. Then, instead of learning sample by sample, they pull mini batches from this buffer to do their updates. This became the standard, really, from Imni et al.'s Atari work in 2015, right up to the complex simulations and robotics we see today.
And this dominance has its justifications, or at least perceived ones. People often talk about sample efficiency, the idea that reusing samples multiple times lets you squeeze more information out of them. That goes back to Reed-Miller in 2005 and was reinforced by the DQN paper. Plus, averaging samples in a batch is thought to give you more reliable, smoother gradient updates compared to potentially noisy single samples. More stable training.
And from a hardware viewpoint, it makes perfect sense. Batch updates are great for modern GPUs. You can feed huge batches, get high throughput. It's like lining up cars at the pump instead of filling one by one. Big efficiency win.
True. But, and this is a big but, this batch approach comes with major drawbacks. Batch DRL is fundamentally computationally expensive. You need huge amounts of memory for those replay buffers, especially with image data. And then there's the processing overhead of managing and running those big batch updates. It's very resource intensive, which, as Yuan and Mahmood pointed out in 2022, becomes a real bottleneck for anything needing low latency or real-time decisions. That batch processing just adds delay.
That's critical. It basically makes these powerful batch methods unsuitable for learning on resource-constrained devices. So you end up with this weird situation. Amazing progress in deep RL in labs and simulations, but effective deep RL under resource constraints. Still largely unsolved in practice. We just haven't seen many truly streaming deep RL applications because the batch methods don't fit that real-time on-device need.
And this leads us right to the core problem. The paper identifies what they call the stream barrier. Sample inefficiency is often blamed, sure. But the authors argue the real killer, the reason we don't see much streaming DRL, is its frequent massive instability. Often, it just plain fails to learn in a true streaming mode. Figure 2 in the paper shows this really starkly. You see other methods just collapse.
Yeah, that really resonates. It makes intuitive sense. Deep RL methods, even in batch settings, already struggle with online updates. You hear about loss of plasticity, the network gets rigid, stops learning new things. Lyle et al. And Dohari et al. Documented this. Then there are issues with poor learning dynamics or just hitting a wall and not improving, or even performance degrading over time. Dohari et al. Saw that too. And these are problems with the stabilizing effect of a replay buffer.
Exactly. Now take away that buffer, go fully streaming, and all those problems get magnified hugely. Why? Because the data distributions, observations, rewards, they're changing constantly, rapidly. There's no stable pool to average things out. Every update is based on a fleeting, unique, non-IID sample. It pushes the learning to its limits. It's like trying to navigate a storm in a tiny boat versus a cruise ship.
And eligibility traces, a classic RL tool for credit assignment, tracing actions over time, but getting them to work reliably with deep neural networks. That's been another source of instability, as Anand and Precup noted. Sometimes they even cause divergence. The whole learning process just explodes, like Viria et al. Found. So yeah, the challenges stack up. This stream barrier isn't just a small hurdle. It's been a fundamental roadblock until now, apparently.
And that until now is the breakthrough. This paper introduces a new class of algorithms, the StreamX algorithms, engineered specifically for stable streaming deep RL.
This is where it gets really interesting and bold. The core idea is learning effectively from only the most recent experiences. No replay buffers, no batch updates, not even target networks usually. They're basically challenging a decade of best practice in deep RL, right? Because the assumption was always streaming deep RL is either unstable or if it works, it's got to be sample inefficient. It's like saying maybe the way we thought deep RL had to learn was actually holding us back.
Precisely. And they don't just say it, they show it rigorously.
Yeah.
They demonstrate streaming deep RL can be stable. And it can be just as sample efficient as batch methods, sometimes even more so. That directly contradicts common wisdom. A really elegant part of the design is that all the StreamX algorithms rely on a common set of core techniques, applied consistently across TD, Q-learning, actor-critic variants. This lets them work with a single set of hyperparameters across diverse tasks. That makes them almost off-the-shelf solutions for streaming DRL. Huge practical win.
Okay, let's unpack these core techniques. The foundation of StreamX. They identified and tackled 3 key issues that usually break streaming learning. First, as you said, instability from occasional huge updates. In streaming, successive gradients can point all over the place. Hard to pick a stable step size. Batch methods average this out.
Second, instability from activation non-stationarity. Basically, the statistics of neuron activations shifting wildly during training makes learning very difficult. And third, improper data scaling. A big issue in online learning with potentially unbounded states or varying rewards. These problems exist in batch too, but streaming with its single sample updates really turns up the heat.
Right, so for sample efficiency, because streaming inherently uses each sample just once they use 2 key techniques. First is sparse initialization, or sparse init, algorithm 1 in the paper.
Sparse init is pretty neat. The idea is to start sparse. Set a large chunk of the network weights like 90% to 0 right at the beginning. The rest get initialized normally, say with LeCun initialization. And the mechanism. Sparse representations create locality. Changes in one part of the network don't mess up other parts as much. This helps reduce forgetting and improves sample efficiency in RL. Prior work by Liu et al. And Pan et al. Suggested this. It's novel for RL initialization, though the core idea has roots in supervised learning, like Martin's work in 2010.
And then eligibility traces. These go way back, rooted in neuroscience, Clough 1972. Basically short-term memory vectors, a decaying trail of recent activity used to link actions to delayed rewards better than simple one-step methods. Better credit assignment.
Exactly. Mechanistically, they accumulate a faded value gradient. Think of the update like zitstill1 plus a wv saint 8. This uses the trace, so it controls the decay. It remembers recent gradients. But it's different from momentum. Two key things. One, traces track gradients of the function output, like the value function. Momentum tracks gradients of the loss. Two, traces reset to 0 each episode. No credit assignment across episodes. Momentum usually doesn't reset.
So the benefit is updates with traces act like multi-step returns, like no return. And they tend to converge better than one-step methods, as Mahmood showed in 2017. And this is the big problem, they've been notoriously unstable in deep RL, often causing divergence, like Viria et al. Found. So integrating them stably is a key part of what StreamX achieves.
Okay, now update stability, a huge issue in deep RL. Atom Optimizer often gets blamed, as Elsayed et al. Discussed. Streaming makes this worse with those fluctuating single sample gradients. To fix this, they introduce overshooting bounded gradient descent, or OBGD.
So the ideal way to avoid huge destabilizing updates is backtracking line search, from Armijo back in '66. The idea is simple. Check if a step will reduce the error before taking it. Don't overshoot. The paper defines overshooting precisely. When the error S changes sign after an update plus S0, you went too far. They define an effective step size. If S1, you overshot. Algorithm 2 shows an ideal backtracking. Shrink the step size S until S is okay. But the killer drawback for streaming deep RL, backtracking needs multiple extra forward passes per step. Computationally way too expensive.
Yeah. Exactly. So OBGD algorithm 3 is their clever, approximate way around this. Get the stability benefit without the cost. It uses first-order Taylor approximation, assumes some local linearity. For TC, the effective step size calculation simplifies to Scareboozer, Opser of WVWVWX. Don't worry too much about the math symbols. The intuition is predict how much the value function will change with this gradient step and compare that to the error. Will this step overshoot the target? They make a further approximation, basically assuming the change in value gradients is somewhat bounded. This lets them derive a practical rule to control the update size without extra forward passes. It boils down to dynamically adjusting the learning rate aux. They calculate a factor m based on the current state, m apps for, and then shrink awk if m is large. It effectively slams the brakes on the learning rate before taking a step predicted to overshoot. Predictive damping. There is also an adaptive version based on RMS prop in the appendix. This OBGD is really a cornerstone for stability.
Okay, then there's stabilizing the activations inside the network. Activation non-stationarity. Sure. As you said, if the distribution of activations changes wildly layer to layer, training goes haywire. Show et al. Showed this. The StreamX solution. Layer normalization, layer norm from Bear et al. 2016. Applied before the activation function to each layer.
And a key detail, they apply it without learning extra scale and bias parameters. Simply, more robust for streaming. The formula, a squirt2 plus OI, just standardizes activations within a layer to 0 mean unit variance. Layer norm is known to be crucial for good performance in tough, deep RL tasks, even with methods like XIC, as Nomen et al. Showed. Plus, it helps fight loss of plasticity, keeping the network adaptable, keeps the internal signals in a healthy range.
And finally, the less flashy but vital part, scaling the data properly. RL is online, environments can have unbounded states, rewards can vary wildly, big targets can hurt training, as Lyle et al. Argued. So how do they handle this data hygiene?
They use standard, proven strategies, scaling rewards, like Engstrom et al., and normalizing observations, like Andrew Kogutz et al. But for streaming, they use Welford's algorithm from 1962. It lets them compute running estimates of mean and variance online without storing all the data. Very efficient. Algorithm 5 shows rewards scaled by the inverse of the running standard deviation, keeps targets manageable. Algorithm 6 shows observations normalized using their running mean and standard deviation. This online adaptive scaling is essential for stability and learning in constantly changing streams.
So putting it all together, sparse unit for efficiency, eligibility traces for credit assignment, the clever OBGD for stable steps, layer norm for internal stability, and online data scaling. They've built this unified framework for Genuinely stable streaming DRL.
Exactly. And it's worth repeating. These algorithms work robustly with a single set of hyperparameters across many different tasks. That's huge. No need for painstaking tuning for every new problem. They're like ready-to-use tools. Speaks volumes at the robustness of the design.
This is really exciting. Okay, let's get into the specifics of the algorithms. How do these pieces fit together? First up, Stream AC for actor critic. Algorithm 7. For problems where you need to learn both a policy, the actor, and a value function, the critic.
Correct. Architecture-wise, it uses separate policy and state value networks. Both use layer norm. Both initialized with sparse in it for that upfront locality benefit. The update flow is continuous, step by step. Start with state S, normalize it, normalize observation. Agent picks action A using policy. Environment gives back next state S, reward R, terminal flag T, normalize S, scale R.
Then the core TD error calculation, ASR plus VSW. And if S is terminal, that VSW term is 0, naturally. After calculating day, update the eligibility traces for both value, SS, and policies. And there's that clever entropy regularization term in the policy trace update, assigned S. Pushes for exploration, especially when the error is large. More surprise, more exploration.
Exactly. Then finally, update the weights. Policy weights and value weights W are updated using OBGD. The update uses the traces, the TD error, and their specific learning rates and OBGD parameters. Thick. Then SASs and the cycle repeats. Sense, act, learn, adapt, all online, every step, truly streaming.
Okay, now Stream Q for off-policy control. Algorithm 8, based on Watkins Q.
Right. This one's for off-policy action value control. Uses a single layer norm action value network, QSAW. Again, sparsing it from the start. The key difference here, especially for off-policy with traces, is how it handles non-greedy actions. If the action A taken was not the greedy action, according to the current CRO chosen via greedy exploration, the eligibility trace ZO is reset to 0. This trace cutting is crucial for stability in off-policy trace-based learning. Stops bad credit assignment.
And the update flow. Similar structure, but the TD error uses the Q learning target, MaxAQ, AW, for the next state value. Learns about the optimal policy even while exploring. And only the Q network weights W get updated via OBGD here.
Right. And just quickly, they also have Stream SARSA for on-policy control, algorithm 10 in the appendix. The main difference, the SARSA signature, is the TD error uses the value of the actual next action A chosen by the policy and state S's. So R plus S, RS, AS, subready now, strictly on policy updates.
And rounding out the family, Stream TD for just value prediction.
Eagles.
Algorithm 9, not for control, just estimating value.
Exactly. Uses a layer norm state value network, VOL, sparsy init, simpler flow, agent just observes states and rewards, calculates, updates, trace, ZO, updates weights W via OBGD, no actions taken by the learning algorithm itself. Pure prediction, useful for forecasting, monitoring. So you see how these core techniques adapt across different RL paradigms, all keeping that streaming stability.
Sounds incredibly solid theoretically. But yeah, the real proof is in the pudding. The empirical results. They start with a direct shot at demonstrating they've overcome that stream barrier. Figure 2 really tells a story.
It's a very stark story. The experiments were extensive, challenging benchmarks. Mujoco Gym, continuous control, humanoids, DM control suite, complex robotics, Atari Games, high-dimensional vision. Rigorous testing, results averaged over many runs. 30 for Mujoco DMC, 10 for Atari, millions of steps. And crucially, if any run for an algorithm diverged, performance shown as 0. Really highlights baseline instability.
And Figure 2 shows that barrier clearly. Classic streaming methods, classic Q, SARSA AC. Terrible performance, often complete failure, but maybe more telling. Streaming versions of top batch algorithms, PPO1, SAC1, DQN1, just setting buffer batch size to 1, they also struggle badly. They hit the same stream barrier. It shows the problem wasn't just old algorithms. Even modern ones fail when forced to stream naively, like putting race tires on a tractor.
But then, the StreamX algorithms, StreamQ and StreamAC, they don't just survive, they learn stably and effectively. Consistently high performance. That's the core finding. They break the barrier. And they're competitive with the original batch versions. Sometimes, astonishingly, even better. Look at the DM-controlled dog environments in Figure 2b. StreamAC gets what they claim is the best-known model-free performance there, significantly beating PPO and SAC. That's a huge claim.
Wow. And Atari Enduro, Figure 2C. StreamQ, outperforms DQN, the classic Atari champ.
Oh.
While using way less memory and compute than DQN, that's not just breaking the barrier, it's showing streaming can be more efficient and effective sometimes. Really turns assumptions upside down.
Which leads perfectly to the next point, tackling that myth of sample inefficiency head on. For ages, the dogma was, streaming must be inefficient because you only use samples once. Batch reuses samples, so it must learn more from the same data. This paper challenges that fundamental belief.
Let's see the evidence. Mujoco Gym, continuous control, figure 3. They compare Stream AC against PPO, SAC, and their streaming versions, PPO1, SAC1. Classic AC was too unstable to even include. The results. Stream AC consistently creams PPO1 and SAC1 everywhere. But here's the kicker. Stream AC is more sample efficient than PPO and Humanoid V4, Humanoid Stand-Up V4, and End V4, more efficient than the state-of-the-art batch method. That's powerful evidence against the inefficiency myth. A real paradigm shift moment.
And it's mostly corroborated in the Minotaur tasks, figure 4. Though with a slight twist, here they compare stream Q as 0.8 against classic Q, 0.8 DQN1 and full DQN. Interestingly, on Minotaur, the classic streaming Q and DQN1 didn't consistently fail due to the stream barrier. This matches what Young and Tian saw in 2019. Suggests Minotaur might just be, well, an easier environment for streaming, maybe less prone to those wild instabilities.
Okay, but even in that less hostile setting, Stream Q.8 still performs comparably to full DQN, and it's better than DQN1 and classic Q.8 in most Minotaur games. So even where the barrier isn't catastrophic, StreamX still holds its own, still shows robust sample efficiency. It's not just about survival, it's competitive.
Next up, sustained stability, critical for real-world, long-term deployment. Can these algorithms keep learning without degrading or breaking over extended runs? They tested this rigorously. 20 million steps for Mujoco AMC, a massive 200 million frames for Atari.
And figure 5 for Mujoco DMC is pretty revealing. Batch methods like PPO showed clear performance degradation over the long haul. SAC degraded in one task and actually diverged completely in the tough dog environments before 20M steps, shows the potential brittleness of batch methods for true lifelong learning. They weren't really built for that continuous grind without resets.
But Stream AC, rock solid, remarkably stable, often continues improving performance over the entire 20M steps. It consistently beats SAC1, PPO1, and even full PPO across all tasks. And crucially, it triumphs in the dog environments where SAC just falls apart. This is huge. It shows superior stability, sustained learning, and real potential for lifelong learning systems that need to run and adapt for long periods.
Similar story on Atari, figure 6.
Very similar. DQN1 fails quickly everywhere. Classic Q.8 struggles badly with instability. The only strong, stable contender against the memory-hungry DQN benchmark on Atari, Stream Q 0.8. And the key finding is pretty stunning. Stream Q.8 outperforms DQN in 9 environments, and it's competitive in others, details in Appendix G. For a streaming algorithm to beat DQN on its home turf, that's massive. Shows you don't necessarily need huge buffers and offline processing for top performance, even in vision tasks.
Okay, so the performance is clearly there. Stable, efficient, often state-of-the-art. Why, the ablation study digs into this, right? Taking Stream AC 0.8 and removing components one by one to see what breaks.
Exactly. This gives us real insight. Removes sparse initialization. The agent still learns, but it's noticeably slower, less sample efficient. Confirms sparseness helps boost efficiency, especially early on. Remove layer normalization. Significant performance drop everywhere. Huge collapse in Hopper and Walker. Shows layer norm is absolutely critical for stabilizing activations and keeping things trainable in streaming.
And taking out the data scaling, or swapping OBGD for a tuned atom optimizer.
Even worse, the agent just fails to improve performance at all. Flatlines.
Shows those scaling steps, and especially ODGD, are completely essential, not just nice-to-haves.
The ablation makes it crystal clear. OBGD has the biggest impact. It's the absolute key to achieving stable learning. That custom step size control prevents the instabilities that killed previous attempts. It's the linchpin.
And what about eligibility traces? We know they can be unstable. Did they actually help StreamX, or was it just carried over? Figure 8 addresses this.
Yes, Figure 8 shows traces do benefit StreamX. StreamX A 0.8 consistently outperforms Stream AC 0, confirms their value for multi-step credit assignment. But, and this is crucial, in classic AC, without StreamX's stability features, adding traces, AC 0.8 versus 0, can actually hurt performance sometimes, like in AMP v4. Shows traces can add instability, but StreamX successfully tames them, primarily thanks to OBGD's careful step control.
Okay, so beyond control, they also tested prediction, using StreamTD on a real-world task.
Right. The electricity transformer temperature, ETTM2 dataset. predicting future oil temperature based on load features and past temperature, a critical task for power grid monitoring. They use general value functions, GVFs, from Sutton et al., 2011. GVFs let you predict arbitrary future signals, cumulants, not just rewards. Here, setting a go 0.99 let them predict about 25 hours ahead. Valuable foresight.
And they used memory traces of observations to handle partial observability in long horizons, built with exponential moving averages, inspired by John Jua et al.
Exactly. Give the agent a compressed history. And the results. Figure 10 shows it beautifully. Starts poor, but learns quickly. The predictions from StreamTD closely track the true oil temperature over time, both early on and later in the 2-year data set. The visual match is really convincing, shows strong predictive power in a real streaming data scenario. Huge practical potential.
So zooming out, broader implications, connections to continual learning seem really strong here.
Absolutely. The instability issues in streaming RL. Very similar to challenges in continual learning, like loss of plasticity and catastrophic forgetting. And layer norm, key for StreamX stability, also known to help fight plasticity loss. Plus, OBGD's step size control might reduce hyperparameter tuning and task interference in continual learning, potentially lessening forgetting. Lots of synergy there.
And OBGD itself is an advance in step-sized adjustment methods.
Definitely. It builds on earlier work by Mahmood et al. And Kearney, extending those ideas specifically to the tricky landscape of deep RL, a big step towards more adaptive, stable optimizers for online learning.
And this really feels like it could revive streaming RL as a field, acknowledging earlier attempts by Elfwing, Young, and Tien.
Right. Those were important early steps, but this paper feels like the first comprehensive step toward reviving streaming deep RL, as they put it, because it provides a robust class of algorithms for prediction, value-based, policy-based control proven across complex benchmarks. It fixed the core stability problem, gives the field a solid foundation now.
And the relevance to TinyML? This feels huge.
Oh, absolutely massive. TinyML is all about ML on tiny, resource-starved devices, microcontrollers. Streaming DRL is the key enabler for on-device training on these things. Continual learning, adapting in real time on tiny robots' sensors. Newman et al. Discussed this. Imagine billions of devices, healthcare monitors adapting to you, robot swarms learning in the field, all running this kind of learning. This research makes that vision much more real.
Truly autonomous, self-improving systems. What about limitations in future work? Where do the authors see this going?
They point out their techniques are broadly compatible with other RL methods. Double queue, dueling, noisy nets. Lots of room to apply these streaming principles more widely. Current work is model-free. A big future direction is combining streaming with learning environment models incrementally for better sample efficiency, like recent model-based batch methods from Hafner et al.
And handling partial observability, always a real-world issue.
Yep. They suggest combining with real-time recurrent learning techniques. Also, more comprehensive testing on off-policy methods using importance sampling is needed, and further refinements to OBGD itself. Plus, the stability insights are relevant for parallel RL2, where distributed updates cause similar issues.
Okay, so wrapping up this deep dive, the core achievement, StreamX algorithms successfully breaking the stream barrier, solving that long-standing instability and inefficiency problem in streaming deep RL.
Precisely. They've shown empirically that streaming can be stable, efficient, and even outperform batch methods like PPO and DQN. This fundamentally challenges the old assumption that streaming is somehow inherently inferior, a major shift in understanding.
And crucially, StreamX isn't just a fix. It's a catalyst to revitalize streaming deep RL. It opens the door for practical on-device, real-time, resource-constrained AI applications. It's an enabler.
So think about it. Stable, efficient, streaming DRL. Agents learning continuously, moment by moment, without huge memory or offline batches. What does that unlock? Personalized healthcare adapting second by second. Robots on Mars learning about new terrain instantly. The frontiers for adaptive autonomous systems just got way broader.
What does it really mean for truly lifelong learning agents? Agents that never stop improving, always adapting. This fundamentally changes how we might design intelligent systems, moving from static models to dynamic adaptability. So we leave you with this. What practical applications jump out to you where real-time, on-device learning would be completely transformative?